Hello, welcome to the course Transducers for Instrumentation. Last lecture we discussed about the basics of optical sensors and some optical sources and optical detectors and how the wave actually travels inside the optical fiber. Today we will discuss some real optical sensors which we use to sense certain measurements. So we will basically discuss three types of sensors. One is the first one is the interferometric sensors. The second one is the distributed sensors, and the third one is the Bragg grating based sensors. So first we have interferometric sensor, which is a point sensor. It means the measurement which we are doing is limited to a confined zone. We have a specially designed a measurement zone where the measurement is taking place with this sensor, and the data comes back to transmitter or the receiver. The second sensor which we are going to discuss is distributed sensor. As we discussed earlier, if we have a large structure and we want to monitor its performance or want to sense certain parameter along the entire length, then we need to have a distributed sensor. It cannot be done by using a point sensor, or we cannot use multiple sensors to monitor the entire length of certain structures. In that case, we need a distributed sensor. The third one is Bragg grating based sensor. This sensor which we can use for the distributed or for the point sensing as well. So these three sensors we are going to discuss. So the first one is interferometric sensor. These sensors provide a very good level of sensitivity. And some of the applications of these sensors are temperature sensor, strain sensor, pressure sensor, and we can measure even the refractive index of liquids as well. So these are some applications of interferometric sensors where we can apply these sensors to make the measurements. The good point about interferometric sensor is they have a very good level of sensitivity. These interferometric sensors are all, again we have four kinds of sensors in these interferometric sensor, which are, the first one is Fabry-Perot sensor. The second is Mach-Zehnder sensor. Or we can call it MZ sensor. The first one we can call FP sensor. The third one is Michelson sensor. And the fourth one is Sagnac sensor. So these are the four optical sensors which we are going to cover in these interferometric sensors. So let's first discuss about the Fabry-Perot sensor. This is Fabry-Perot sensor. Or we can call in short FPI sensor. So this is generally composed of two parallel plate reflecting surfaces. Which are separated by a certain distance. And the interference occurs due to the multiple superpositions of both reflected and transmitted beams. So in this FPI sensor, we have two interfaces, and the wave travels, let's say wave is traveling in x direction, and then we have two interfaces or two discontinuity in the path of this optical wave. This wave is going to reflect at both of the interfaces. Some part will be reflected back at first interface, some will be transmitted, and some part of this transmitted wave will again get reflected at the second interface. So when we look at the origin, we get two waves. One is the reflected at interface 1 and the second one is reflected at interface 2, and there will be a time difference between these two waves because this second wave need to travel a extra distance of separation. What this the separation is between these two discontinuities. So accordingly there will be a phase difference between these two incoming between these two reflected waves, and based on that phase difference we can determine what is the time taken by the wave in between these interfaces. So let's say we have a optical fiber here, this is cladding, and inside this we have core, and the wave is traveling in this optical fiber. Now we have first discontinuity here. Let's say this is my discontinuity here, and my second discontinuity is at this point. After this we have again this optical fiber, and the distance between these two interfaces is L, which is a known number. Now my wave is coming in from the left inside this optical fiber. The first reflection will take place at this interface. Some of the wave will go back into the core, which will be reflected back at interface 1. This is interface 1. This wave, let's say we call it reflected 1. Some part of this wave will be transmitted into this medium and it will be reflected at interface 2. This is interface 2, and this wave will go back here and we receive another wave which is reflected at interface 2. Let's say call it R2. So here we can see the wave R1, it traveled less distance compared to R2 because R2 has traveled twice the length L, which is the separation between the interface 1 and interface 2. So if we plot this R1 and R2 on the same scale, this R2 will be time delayed compared to R1. This will give us the phase difference between these R1 and R2. Now this phase difference depends upon how much time the optical wave takes within this cavity, which is of length L. Now this cavity, it may be filled by air or it may be filled by some other liquid. We can pour some liquid into this cavity, and because of the different refractive index of that chemical or whatever we pour it, the velocity of wave will be different, and accordingly the phase difference between R1 and R2, that will be different. So based on the how much the phase difference we get, we can detect what material is poured into this empty cavity. So this is the working principle of this Fabry-Perot interferometer. This is the case where we have this is extrinsic type. It means the fiber is cut in between and we have made a artificial cavity here, and we can pour liquid here. We can pour chemicals here, and based on the difference of refractive index, we get different phase difference between R1 and R2. This is the case of extrinsic type. we have cut the fiber here. The another case we can make intrinsic type, where we are not cutting the fiber, we have a single fiber only. So this is a single fiber, and now within this fiber itself we make discontinuity at this point and at this point. This we can do by laser scribing and or many other methods. So this case is intrinsic type, where we are not cutting the optical fiber. And here, when we are sending this optical wave here, some of the part will be reflected at first interface and some part will be reflected at interface 2, and at the input side we get two waves, one is R1 and R2. So this is how if FPI sensor look like. We can have extrinsic type as well, where we have a separate cavity where we can pour the liquid. So this can work as a refractive index meter. We can detect the material based on the refractive index of that material. The other is intrinsic type, where we are not cutting the optical fiber, and this can also be used as a temperature sensor. For example, because when the temperature increases, this length, which is a fixed number here, we know, because when we laser scribed it, we know this number very precisely, this L. If the temperature changes, this length of this optical fiber changes, and based on this change in the L, R1 and R2 will get different phase differences, because R2 is the one which has to travel this length 2 times. However, R1 is fixed in the in return path. So R2 always changes with change in the L, which is a function of temperature. So this intrinsic type FPI sensor we can use as a temperature sensor. The phase difference of this FPI sensor is given by the delta FPI is equal to 2 pi by lambda into eta into 2L. So this is the phase difference we get in case of FPI sensor. Where this lambda is the wavelength of incident light, this eta is the reflective index of cavity material, and L is the distance, the physical length of cavity. So this is the formula for getting how much phase shift we get. We can see this depends on 3 parameters. One is the lambda, what frequency or what wavelength we choose for the optical optical wave, light wave. So that is generally fixed by experiments. We generally choose a single optical source, and based on that our wavelength is fixed. So this is generally a fixed number. The second parameter is the refractive index of cavity material. So what we put in this cavity, the refractive index of this material changes the phase difference. So according to this Ri of this cavity material, we get the phase difference delta. And the other property, other parameter where this phase shift depends, is the length, which is the physical length of cavity, which is generally fixed unless case of temperature sensor. This length of the cavity is generally fixed and known number. When we make this sensor, we generally know how much is the length of this cavity. So this is again a constant number. So our phase shift depends on how much is the Ri of cavity material, and we can make some kind of chemical sensor using FPI sensor. So this FPI sensor are appropriate to measure the refractive index of liquids because the measurand is the chemical actually in this case. So because the measurand can access the cavity very easily. So we have a cavity here in FPI sensor, and we can pour our liquid in that, and based on the refractive index of this material what we pour in, we get different phase shifts. So if we plot the graph between the refractive index and the uh, phase difference, it will look like something like this. First we plot the intensity, normalized intensity on y axis, and the round type on the round trip delay this is nothing but the phase difference. So we see based on the different materials we get different peaks here. Let's say this is one peak we detect. This is for, let's say, ethanol. The other material can be like this, where we have acetone. Some other case we can have like this, where the liquid we pour in the cavity is water. So based on the different liquids what we pour in the cavity, we get different peaks in this graph, which is intensity versus the round trip delay. And if we plot this measure and refractive index, which is our actual measurement, this is measured refractive index of liquid versus what we actually know that liquid, let's say labeled refractive index. This kind of sensor performs pretty well, and we can see kind of a very linear fit with the measured data. Let's say this is the measured data and this is the blue line is kind of the labeled Ri. So we get a very good fit between the measured and the labeled Ri, and this FPI sensor can be used as a refractive index meter of liquids. So this is FPI sensor. Next we discuss the Mach-Zehnder sensor or the MZ interferometer. We can call it MZ sensor or MZI sensor. These are commonly used in diverse sensing applications because of their flexible configuration. These are commonly used in diverse sensing applications. Because of their flexible configuration. These MZI sensors have very flexible configuration, and they have basically two arms. One arm is considered as a reference arm, which we do not change, and the other arm is called the sensing arm, where we apply the measurement. And the difference between the parameters of these two waves, one is traveling in the reference arm, one is traveling in the sensing arm. So based on the difference between these two waves, we figure out what measurand is applied at MZI sensor. So this sensor, this MZI sensor has two different arms. Which are the reference arms, and the sensing arm. Here this reference arm is kept isolated from external variation, and only sensing arm is exposed to this variation. So here we have one fiber which is coming in, and we use some optical coupler to split the wave in two directions. So this splitting is done by 3 dB coupler. So here in this diagram we have a wave which is coming in from x direction, and we use a 3 dB coupler which splits this wave, this single incoming wave, into two different paths. Of course the intensity will be half, because half of the wave come into the upper arm, which is, let's say, called reference arm, and the half of the wave will go into the lower arm, which is sensing arm. Now the reference arm, we do not expose it to the measurand, only the sensing arm is the one where we apply the measurand, for example temperature, which is the sensing arm is exposed to, and reference arm is kept isolated. So because this is the single wave which was split at the input, the sensing arm, the parameter of this optical wave will change based on the measurand, and at the destination where we get both of these waves, one wave will be different than the other, and because we send the single wave at the input, we know by the difference how much is the difference between the parameters. Based on that difference in the parameter, we can detect what is the measurand which we have applied on the sensing arm. So we have here, this is reference arm, where which we keep isolated, and this is the sensing arm. And the wave is actually traveling here as well as here, and here we apply the measurand. So these waves, one will be impacted by measurand and the other will be isolated. When they reach here at this far end, we again use a 3 dB coupler here, and this 3 dB coupler is kind of reciprocal. It can split as well, and it can again combined also. So this 3 dB coupler again combine both the waves back, and here at the output we get a single wave. Now we have two waves in this. One is, let's say, R1, which is from the reference arm, and one is the R2, which is from the sensing arm. This R1 is from the reference, and this R2 is from the sensing arm. and based on the difference in these two waves, we can detect what is the measurement is applied. For example, the temperature is applied, then how much is the temperature is applied, that we can measure using the phase difference between these two, reference wave and the sensing wave. So this is how this MZI sensor works. Now there are many ways of creating the interference in between the core and the cladding of this optical fiber. There are multiple ways by which we can make the interference in the optical waves. So we can discuss some of them. For example, we have one fiber. Inside this we have core and the cladding. So let's say this is core and this black is cladding. If we make certain discontinuities, for example, we put some grating here in the core, so if in this fiber we have introduced certain discontinuities, which is the fringes here, whenever this optical wave sees a discontinuity, it tends to kind of refract at that interface. So this wave, let's say this optical wave which is traveling here, this will be refracted into the cladding. Some part of this will be refracted into cladding, and some part will be remain in core, and they will travel separately in core and cladding. However, this fringes, they work in the reciprocal way. When these waves reach here, they can again be combined by these fringes or these discontinuities, and we get a wave here at the output, which is a combination of the wave which is traveling in core. Let's say this is our core plus our cladding. So some part of this optical wave was traveling in cladding, so that will also be recombined back at interface 2, and interface 1 is splitting this wave into core and cladding. So this is one way of making interference. The second can be, we have optical fiber and some section of this optical fiber is misaligned with rest of it. Inside this we have this core, so we can see here some part of this optical fiber is misaligned and we have discontinuity, and let's say this is discontinuity 1 and this is discontinuity 2. These kind of discontinuity also act like a refraction at this point. So some part will be traveling in the core and some part will be refracted into the cladding, and again at the interface 2 this wave will be combined back here, and we get this R core plus R cladding. So any discontinuity in the path of light, it causes the optical wave to refract to some other media. This is second case. We can have multiple type of cases. For example, in case number 3, we use certain grating. We can make certain grating inside these optical fibers. So here we change the material of this optical fiber here and here. So now if the wave is traveling this side, this wave will be splitted here by this discontinuity. Some part will go into core and some will be in cladding, and again by the second discontinuity, which is here, this will be combined back into the core, and we get our core plus our cladding. So these are some of the ways by which we can create the interference in optical waves. Some of them are preferred because, for example, the grating which are easy to make using laser sources, we can very precisely make these gratings into the optical fiber, and we can create these interferences. So this is a good way of splitting these two waves from a single wave. So coming back to the MZI sensor, we can see a particular case where this MZI sensor we can use for temperature measurement. So in this MZI sensor, we take a optical fiber and we create multiple gratings at the input side and some at the output side with a known distance L in between. This is D, and this optical fiber we feed using a light source. And on the other side we have a detector. Now this is the assembly of MZI sensor. We have a fiber where we have precisely put this grating at the input side and at the output side with a distance which is known and which is fixed L. Now we expose this assembly to the temperature which we want to measure. These gratings what we have put, we have seen in last slide, these gratings can actually split the wave into core and the cladding. So the wave coming in at the left, this actually gets split into core and cladding and again combined back at the output. Between the core and cladding is combined and goes to the optical detector. Now there is a difference between the temperature expansion of core and cladding material, and that difference gives rise to the difference in the phase between these two waves, which is one is traveling in the core, one is traveling in the cladding, and the interference fringes are formed. So when a part of cladding mode is recoupled to the core mode, the interference fringes are formed. And the phase change is given by K into delta N effective and the L, which is the distance between these two fringes. So this is the formula to calculate the phase difference, and if we plot this transmission with respect to the wavelength, on the y-axis we have transmission, and on the x-axis we have the wavelength. This looks something like this. Let's say this is one wave. If we change the temperature, this transmission coefficient actually changes. So we have different these different minimas for different temperatures. If we are changing the temperature here, and if we plot this wavelength as a function of temperature, which is our actual measurement, on y-axis we plot the wavelength and x-axis we put the temperature. We can see a fairly linear graph where this wavelength is linearly changing with the rise in the temperature. This graph is very linear. So this is a typical output for MZI sensor, where we can see the output, which is the function wavelength, which is very much linear to the temperature change. A linear change is always desirable in making the sensor. So this is MZI sensor, which we have used as a temperature sensor. Here this length actually is changing with temperature. There is a elongation in the, or the expansion in the this optical fiber length because of the temperature expansion, and this length, this change in the length or the expansion in the length is giving rise to the difference in the wavelength. So this is MZI sensor. Next we discuss the Michelson sensor. Or MI sensor. In MI sensor, this is very much similar to the previous sensor. In previous sensor, we have two arms. One is the reference arm, one is the sensing arm, and of this reference arm is kept constant and sensing arm is exposed to measurand. At the output, we again combine these sensing and reference arm to get a common output. If we see closely, this structure is very symmetrical. From the input, we split up and again we combine to get the output. If we cut this structure in between and put a mirror, is a physical mirror, then this wave will be again reflected back to the origin, and because these waves can travel in both the directions, there will be no kind of problem in cutting this structure into half. So this MI sensor or Michelson interferometer is very similar to this MZI sensor. The basic concept is same. Which is interference between the beams in two arms but each beam is reflected at the end of each arm. So in the MZI sensor, we have this optical fiber and we use a 3 dB coupler to split the wave into two, and one we call the reference arm, the second is the sensing arm. This is 3 dB coupler. This wave comes from the left. Now instead of completing these arms, we put some sort of mirror here. This is actual mirror where we are reflecting the light. This light goes here and again reflects back from here. The same thing in the sensing arm. It goes and reflect back here, and 3 dB coupler is also reciprocal, so it can again combine these reflected waves and send it back to the origin where we can detect it using optical detector. So now we see we need not to complete this whole assembly, and we need not to use another 3 dB coupler at the output. We just kind of reflect all the waves back. One is the reference arm, which we again keep isolated. So this is isolated, and this is the sensing arm, which where we apply measure end. And except this change in the structure, all the phenomena of this MI sensor is very close to the MZI sensor. We can use this sensor in a similar way as MZI sensor. The fourth sensor is the Segnex sensor, or Segnex interferometer. So these Segnex sensors, these are very much of interest nowadays because of their robust configuration, easy fabrication, and we can use in multiple environments. So these Segnex interferometric sensors are of very much interest nowadays. The basic structure of these SI sensor is something like, we have a optical fiber which is coming in here, and then we have a 3 dB coupler which splits this wave which is coming from this fiber into two parts, and this fiber, both the end are connected to a single fiber. So in this way, this is a circular loop of the fiber, and again we have a fiber going out. This is our input and this is our output. This is 3 dB coupler. Now from the input, let's say one wave is coming here. This is splitted by this 3 dB coupler. Half of the wave will go in this direction, half of the wave will go in this direction. So we can see in this assembly, half this wave is split by this 3 dB coupler. Half wave will go in this direction, it means it is moving clockwise, and the other wave is moving anti-clockwise. So both of these waves, they are originated from the same wave, but now they are traveling in opposite direction, one in clockwise and one in anti-clockwise. So right now the path difference in both the waves is same, so there will be no phase difference at the output. Now what we do, we take this assembly and rotate it. This whole assembly is now being rotated. Let's say this is the rotation of this whole assembly. Now what will happen, the wave number 1, for example, this is the wave number 1. When the rotation is in opposite direction, this wave will take less time in reaching from one end of this fiber to the other end, because by the time it it reaches the other end, the assembly moves in the opposite direction, so the end point actually comes nearer. However, this wave number 2, it takes longer time in reaching from start to end, because by the time this wave reaches at the far end, this assembly rotates in the same direction. It means the end point shifts further away from this wave, and it takes more time compared to the wave 1, which is taking less time. So because of this difference in reaching the end point, there is a phase difference in between these two waves, wave number 1 and wave number 2. So these are originated from the same wave, so we can compare the phase difference of wave 1 and wave 2 and see how much is the speed of rotation of the assembly. So this, the faster we rotate, the more will be the phase difference between wave 1 and wave 2. So these SI sensors are of great interest nowadays, due to simple structure and robustness. In this, a beam of light is split and sent into opposite direction on return. On return to the point of entry, the two light beams are allowed to exit this ring, and they undergo interference. And the phase difference delta phi is approximated as 8 pi upon lambda into omega into A, where this A is the area and omega is the frequency of rotation. So A is the area of this loop and omega is the frequency of rotation. This phase difference here, delta phi, is a function of this omega, or how fast the assembly is being rotated. And if we plot this phase shift, with angular velocity. On the y-axis we have phase shift, and x-axis we have angular velocity. The graph looks something like this, which is the phase shift with angular velocity, and we can see that phase shift is actually increasing with angular velocity because this delta phi is proportional to w, the or the omega, the angular velocity. So today we discussed interferometric sensors, which are basically 4 types, and we discussed each 4 of them here. So this is all for today. Thank you.